because the loading is basically by what? By the mass and also the interaction between the mass and the spring. There's no external force, right? So if I do that, of course, it's assumption. If I set P minus P to be 0, just set this to be 0, and the Garber equation becomes M times S double dot plus Ks equals 0, and the solution is this. S of t equals to S naught times cosine omega n times t plus S naught dot over omega n times sine omega n times t. So here I have to give you some definition here. First, what is omega n? Omega n is what we call the square root of spring constant K divided by mass. This is what we call natural frequency. Very soon, as an engineer, either civil or mechanical, you must come across this term, natural frequency, or we call it fundamental frequency. You will have to learn how to calculate it. But by definition, if there's no damping, fundamental frequency equals to the square root of stiffness divided by mass. In other words, if you're trying to play with a spring, but the spring is very strong, the fundamental frequency of the spring is going to be very, very high because the value of K is great. Now here, S naught is what? What we call S naught is initial displacement. Of course, S is displacement. S naught means displacement at T naught. So S naught is nothing but initial displacement. Now what happens to S naught dot? S naught dot isn't it just the V naught? Right? Because S dot means the time derivative of displacement. So time derivative, initial time derivative of displacement is just initial velocity because time derivative of displacement is velocity. So S dot naught is just V naught. So this one is just initial velocity. And what else do we need to know? What about T? T is time. Of course, just be careful that this is the whole thing. It's not cosine omega n times t, but it's a cosine omega n times t. So it's a cosine of omega n times t. What's t here? T is time. And time, of course, is in the unit of usually seconds. And displacement is usually, linear displacement is in the unit of either meters or inches or feet. Initial velocity, of course, you know, right? Is in either meter per second or inch per second or feet per second. Now, what about the unit for this fundamental frequency? Omega n. In fact, you already know how to calculate omega n because if I tell you what a K, you know how to find the K, right? I tell you the mass and I tell you the K, you can calculate omega n. So this is fundamental frequency, has a unit in what we call 1/second, and this is constantly defined as hertz, or sometimes we just call it Hz. The unit of fundamental frequency is in hertz. Now, be careful here. This omega n actually has two different types of units. If you use omega n, by putting these numbers into here, is actually will give you radians per second. So this result is going to be radian hertz, not just hertz. And why is that? It's because this omega n is what we call angular frequency. or sometimes I call it radiant frequency. And there's another frequency that we talk about in Hertz. That one is what we call temporal frequency. And they are related by omega n equals to 2 pi. This is the conversion factor, of course, times Fn. So the ones that we are used to in everyday life is actually this Fn. So Fn is temporal frequency. And this temporal frequency is in the unit of 1 over second or hertz. So the last piece in today's lecture is be careful that there are two different kinds of frequencies. You should know. One is angular frequency, the other temporal frequency. Temporal frequency is in the unit of hertz. Angular frequency is in the unit of radian hertz. Notice that that's why I said this is angular, and they are related by this factor 2 pi. Okay, now I'm not sure if we have time for the final review, but I can just briefly walk you through the process in here. Remember from the very beginning, we start with an introductory overview saying that dynamics is comprised of two major components. One is kinematics and the other is kinetics. Now, in each one of them, you can also consider that whether we have kinetics and kinematics in linear motion, angular motion, or general motion. That means the combination of two. So for kinetics, or let's start with kinematics. For kinematics, you have linear motion in kinematics, angular motion in kinematics, and general motion in kinematics, right? The same thing applies to kinetics. Linear motion in kinetics, angular motion in kinetics, and general motion in kinetics. That is the highest level of understanding in dynamics. You should know that there are different applications. And when we solve problems, sometimes we use techniques from kinematics, sometimes we use in kinematics. We use these two exchangeably. And we also use not only the energy principles, we also use principle of impulse and momentum. Remember? So what's the difference between these two? If you want to know the time information, you have to use principle of impulse and momentum. Whether it is linear impulse or momentum or angular impulse and momentum, you have to, if you want to know the time information, you have to use principle of impulse and momentum. Rather, if you don't want to know the time information, you just want to know what's the change in velocity, then you use energy principle, which is T1 plus V1 equals to T2 plus V2 plus summation of total work. That's energy principle provides you those change of information. But the fundamental drawback in energy methods is doesn't give you time. The energy method doesn't give you any information in time. So you must want to know how long does this car travels from maybe 50 miles per hour to 80 miles per hour. You cannot figure it out by using energy method or the energy principle. You have to use principle of linear momentum to figure it out.